Now let's talk about quadratic functions and their graphs. So what is the general form of a quadratic function? A quadratic function, and there are several forms, by the way, of these quadratic functions. We are interested for now at this moment what we call the polynomial form. The polynomial form of the quadratic function is f of x is equal to ax squared plus bx plus c. That is what we call the polynomial form. And in this form, a cannot be 0, because if a is 0, notice we reduce this down to a linear function, and we don't want that. Now, the graph of quadratic functions are called parabolas. Okay, so the name of the graph is parabola, which the literal meaning of parabola is placing besides. That's what the literal meaning is. So here's the shape of the parabola. The parabola could either open up or downward depending on a. If a is positive, the parabola opens upwards. If a is negative, the parabola will face downward. Okay, as far as the curvature of this function goes, because the function opens upwards, so the curvature, or we call it the concavity of that curve, is facing up. Therefore, we can say that the graph is concave up, and the one next to it, therefore, is concave down. All right, so we have that now. What else do we need here? Let's see. Oh, the low and the high points. In the case where the parabola opens downward, the high point is a max. The high point is called a vertex. The vertex is the peak of the parabola if the parabola opens downward, and that's exactly where the max occurs. In the case where the parabola opens upward, then the vertex is going to be the low point, therefore vertex is going to be a minimum. Okay, and the vertex, I'm using V for vertex. Every parabola has an axis of symmetry. This axis of symmetry is not part of the graph, but more of a reference. It's a vertical line that runs through the vertex of the parabola. And that's the line about which the right branch is mirror image of the left branch, and vice versa. So that's where we say the symmetry occurs. And for that reason, this is called the axis of symmetry. Okay, so we have that. Now the axis of symmetry of the parabola here runs through the vertex. Question is, what are the coordinates of the vertex, right? If we have that, then we can find or write the equation for that vertical dotted line. Now it turns out the coordinates of the vertex, if we call them x, y, these coordinates for the parabola occur at negative b over 2a. And there is a formula for y also, like it is for x, negative b over 2a. But usually we don't write that formula. I will, for reference, write it for you in a moment. But usually we just do f at that point. That means we evaluate the function. You simply plug it into the function for x, whatever that first component is, to get the second component. But if you are into the y component of the vertex, the y component is given by 4ac minus b squared divided by 4a. I don't recommend memorizing or working with that, although you could. You're welcome to, but not necessary. Okay, and there we have the coordinates of the vertex. Now, there is a second form. All in all, there's about half a dozen different forms of quadratic functions, but the second form that in this lecture we are interested in, we're going to look at, this second form is what we call the vertex form. The vertex form, and it's called vertex form because if you have the correct form, you can actually identify the vertex from the graph here. So the vertex form looks like this. We have f of x, and that's going to be equal to a x there's a subtraction symbol here, minus. Okay. And then I'm going to use h squared and then plus a k, and that is the vertex form. H and k indeed are the coordinates of the vertex. So the vertex is at h, k. Okay, and in this case, you don't need a formula for h and k like we did up here. We had a formula for a vertex that would be the h and k, by the way. But we get it directly from the form of the function, the way the function looks. Well, by the way, up here, I forgot to mention, I did say we can find the equation for the axis of symmetry once we know the coordinates of the vertex. The equation for the axis of symmetry x is the h component, the x component now of the vertex. And there you go. That's the equation for the axis of symmetry. All right. And that's what you have in here with the vertex form. So if I have a general parabola, let's say in HK, standard HK form, suppose I have a parabola that looks like this. Here's my axis of symmetry that runs through the vertex. This would be H, and here's where K is. And here's a case where A is positive, right? Because my parabola is opening upwards. And the equation for the axis of symmetry is x equals h. Exactly like it was on the one above. All right. So let's take a look at some examples here. So for my first example, this is the first example. Let's look at this function. I'm going to have a function that is in HK form. Okay, x plus 2 squared minus 2. Now to be exactly in the HK form, that means I need to have a minus here and a plus here, right? Exactly like you see up there. Okay, so I went ahead and created my minus and pluses there. And the negative 2, I can write it as a plus negative 2. And the positive 2 in here within parentheses, I can show that as double negative, correct? Negative of negative 2 is 2. So there you have it. Again, doing so will enable me to correctly identify the h and k. So h is negative 2 and so is k. The vertex has coordinates to negative 2 and negative 2. All right. And again, it may be easy for you to see, instead of going through rewriting it, which I recommend you doing it, you can also see in its original form. When I have x plus 2, think about what makes x plus 2 0. X has to be negative 2, correct? And notice that is your h. So your h is always opposite of what it seems to be, the number inside parentheses. If it's plus 2, your h is negative 2. All right, now let's say I want to graph this parabola next. So to graph it, I'm going to use my library of functions. Okay. Now the vertex is in the third quadrant, negative 2, negative 2. So I'm going to go like this. Suppose this is my coordinate axes. And the basic parabola, all right, the basic parabola looks like this. Again, that's from the lecture on library of functions we had. We know that's what x squared looks like. Now, using transformation of functions, again, we talked about this in chapter 2. If I have x plus 2, well, in x plus 2, that means I'm going to have a horizontal shift to the left 2 units. So what's 0 now moves to the left. It's at negative 2 now. So this would be now x plus 2 squared. The negative 2 that you see on the outside, that would be the k here. This negative 2 indicates a vertical shift. Okay, vertical shift, and if it's negative, we move down 2 units. So I'm going to go down 2 units. Let's say that's negative 2. And then just redraw the parabola at that point, and that would be the final graph. Right there. See that? And the axis of symmetry, of course, a vertical line through it. Here's the vertex. The equation for the axis of symmetry is x equal negative 2. In general, that's x equal h. All right. Now again, this horizontal vertical shifts that we talked about, let me see if I can find that for you. Let's see, transformations. Yeah, exactly where we are. This is where, remember, it's a lecture on section 2.5. I think that's lecture 5. And here's where we talked about all these shifts. So the one in my example I used was this one. I shift the parabola to the left, and then k was negative 2, so the vertical shift was down 2 units. Okay, so it's helpful to go through this. Alrighty, we're done with that example. Now let me make an example where what if we do not have the HK form? So in my next example, we're going to look at the case where we actually do not have the HK form. So for this one, I'm going to go f of x is equal to x squared plus 4x plus 2. Okay. Now notice this is in polynomial form, correct? So in polynomial form, if you want to change this to the HK form, we need to complete the square. Okay. Or for this particular one, let me see. Yeah, I thought that's the square of a binomial, but it's not. Okay, so here's how we complete the square in x. We're going to group x squared plus 4x, and we're going to brush aside the 2. All right. Now, when we do complete the square, by the way, it is very important that the coefficient in front of x squared has to be a 1, and it is in this case. If it's not, once you group x squared and x, then you would factor the coefficient. If it's different from 1, you need to do a factoring step. All right. So the question is now, I need to add something within parentheses. And if you recall from, again, what we're doing here is called, again, completing the square method. So for completing the square method, again, what we need to do is we need to add something in here. What do we add? What gets added is half of the coefficient 4 on x, and then you square it. Don't forget the squaring part. Half of 4 is 2, 2 squared is 4. Now, if you noted, I just added the number that wasn't there a moment ago. So how can I undo what I have done? Well, if I add 4 to one side of an equation, I can subtract 4 from the same side, correct? But if, or you can add 4 to both sides, but I want to keep my f of x intact. I don't want anything next to that. Cool. At this point, what we have in here in parentheses, we call this a perfect square trinomial, and that means I can write that expression as a square of a binomial. What does the square of a binomial look like? Well, half of 4, 2 is what goes in here. And don't forget, you square the binomial. You have to square it. Otherwise, it's not the same as the trinomial. And next to that, 2 minus 4 is negative 2, and I have the HK form. It looks exactly like the one we have up there, doesn't it? Okay, so the graph is above. It's just coincidental. I'm just going to say graph above. So I don't have to walk you through the same steps. But at this point, if the numbers were different, you identify HK and you decide the parabola opens up and down, and then you just graph it. Okay, or you can use transformations. Alrighty, let's take a look at another example. For this one, and let me go in polynomial form. F of x is equal to x squared plus 2x plus 1. Now for this one, let's say we want to find the vertex, the axis of symmetry, and determine whether it's concave up and downward. And let's do the xy intercepts of this one, and then we will graph the function. Okay, and maybe even do a domain and range, and we do increasing, decreasing, everything that we've done with functions. Let's do with this one. So first of all, the function is in polynomial form, by the way. You don't have to go to HK form to graph this. Remember, we had a formula. The vertex is negative b over 2a and f at negative b over 2a. I haven't used that yet, so let's use this. Let's identify our ABCs. A is 1, the coefficient on x squared. B is 2, and C is 1. Okay, now the vertex H is negative b over 2a without completing the square. That's going to be negative 2 divided by 2 times 1, or negative 1. H is negative 1, so far we know this. Now the y component, you do f at negative 1. See, that's what I said. You don't need a formula. Just plug in negative 1 for x. And f at negative 1, which is negative 1 quantity squared plus 2 times negative 1 plus 1. You plug it into here. Okay. And what is this going to give me? That's going to give me 1 minus 2 plus 1, or simply 0. Therefore, the coordinates of the vertex are at negative 1, 0. Negative 1, 0. So here's x, there's y, here's negative 1. Okay, and let me draw this a little more straight. Now, what else do we need here? Let's say we got the vertex, so that's going to be the vertex. Now, what is a, by the way? A here is 1, correct, which is positive. So the parabola is going to open upwards. So at negative 1, it's going to open upwards. The y-intercept, because I need to know whether the parabola goes this way, this way, this way. I need to graph this accurately. So let's find the y-intercept. The y-intercept is when x is 0. So we do f at 0. That makes it 0 squared plus 2 times 0 plus 1, or 1. So the y-intercept is going to be at 1. Let's say this is 1. X-intercept is at negative 1. And there you go. So I can graph this branch of the parabola. Right? Now the other part, the other branch, I can use reflection about the axis of symmetry to get that one. Reflect this point across, and I come over here. And then just redraw this one. And there we have the graph of this function. Okay, and the equation for the axis of symmetry is x equals negative 1. We did the y-intercept. Let's do the x-intercept. For x-intercept, and I can see x-intercept is at negative 1, right? But just to kind of show you the general procedure, for x-intercept, we set f of x equal to 0, and then we solve that equation. Okay, so we have x squared plus 2x plus 1 equals 0. Now, to solve this equation, we can use the quadratic formula to solve it, right? Or we can maybe factor this one. Let's see. If we go factoring, x minus 1, x minus 1. You have repeated factor. Remember how the factoring works. You need two things. The first two terms multiplied to x squared. And then the first one and the last one, that the outer terms, negative x, the inside terms, negative x makes negative 2x. Yeah. Wait a minute. Yeah, this is actually, let me see for this one. Hold on. Okay. Well, let's see. Notice the middle term is negative 2x, but I want it to be positive, so we're close. We just have to tweak this one. That's typically how we factor these trinomials, right? So it should work now. And there you have it. So I did FOIL, in other words. When you do FOIL, you get x plus 1, which is a repeated factor. I can write it as x plus 1 squared equals 0. That means x plus 1 must be 0 or x is negative 1. So that's another way to get your x-intercept. All right, so we did our x-intercept, y-intercept. We did finish the graph of this function. Let's see. As far as concave down or up, this thing is going to be concave up because it's opening upward. It means the curvature is facing upward like that in that direction. That's what that is. Did the axis of symmetry. Let's see what else. Let's do the domain and range of this one also. What is the domain of this? Well, because it's a quadratic function, domain is all real numbers. In other words, x can be anything. The range are possible y values. From the graph, notice the range are possible y values start at 0 and work higher. There is no y down here, right? Because there is no graph. So my range is going to be from 0 on the y-axis to infinity on the y-axis. And let's do our increasing, decreasing, the function. And for increasing, decreasing, if you remember, we go from left to right on the x-axis. And as you go from left to right, it looks like the graph is dropping. Let me just put decreasing. Function is decreasing from negative infinity on the x-axis up to negative 1. Correct? Up to negative 1. And then it will be increasing thereafter. It's going to go increasing from negative 1 to infinity on the x-axis. All right, and that's this part right there. See, it's going to increase as we go from negative 1 to infinity. All right, we did that part also. Where is the function positive or negative? Let's do that also. F of x is greater than 0. Now, f of x is y. Y is greater than 0. Well, if y is greater than 0, that means the graph sits above the x-axis. And if you look at the graph of this thing, it's always above the x-axis, right? So the function is positive from negative infinity to infinity. Is the function ever negative? No. So that's it. That would be a complete example of something in this section. And maybe we'll do one more just to practice. Yeah, let's do one more. Next example. Oops, sorry, didn't mean to do that. Okay, not sure what happened. Okay, in this next example, something similar to what we just did, but a different function. One that the coefficient is not 1 in front of x squared. Let's say that's 3x squared plus 6x plus 2. We want to do exactly what we did earlier. So if you want to complete the square, by the way, here's how we would do it. You go 3x squared plus 2x. See, that's when I group the x's together. Move 2 away from the action. What do we add inside? Half of the coefficient on x squared. Half of 2 is 1. 1 squared is 1. So I'm going to add 1 inside. I'm going to subtract 1 from the same side. However, that would be incorrect, wouldn't it? See, up here, you say, well, you did it up there, and I did. Where was it? Yeah, right up here. When we complete the square, I added 4, subtracted 4. And the reason is because the coefficient outside of x squared, outside of the trinomial, is 1. Let's check this one out. Because of that 3 on the outside, remember when you redistribute 3x squared, we pick up that term. 3 times 2, 6x, we'll pick up this term. The 2 is here. Now what about 3 times 1? Isn't 3 times 1 3? So to the right side, I really added 3. It looks like 1 in parentheses, but that 3 on the outside will force a distribution to 1. And therefore, that's going to make it 3. As a result, I need to subtract 3 from the right side, not 1. So you got to be careful. When there is a number outside parentheses, that's always going to be the case. All right, now I can write this in the HK form. The HK form is 3x plus 1 squared. 2 minus 3 is negative 1. Now I can identify the HK, correct? That's why I like the HK. You don't have to use negative b over 2a. So h is opposite of what it seems to be in parentheses. H is negative 1. K is what it seems to be, negative 1. And there we have it. Negative 1, negative 1. That's the HK. Good enough. Now once we have the vertex, we can actually kind of graph this parabola. I say kind of because I need to know the xy intercepts too, if they're above or below the x-axis. Okay, negative 1, negative 1. Let's say that's what that is. The vertex is at that point. Negative 1, negative 1. Now, the parabola is going to open upward, right? Because a is 3. This number, that's a equal 3, which is positive. So parabola is going to open upwards. There you go. Again, I need to know where is it going to cross on the y-axis. So I need to find my y-intercept. The y-intercept, that's when x is 0. We do f at 0. We get 3 times 0 squared plus 6 times 0 plus 2, and that's just 2, because these are zeros. So when x is 0, y is 2, let's call that 2. Okay, so the parabola is going to have to go through that opening up and going through that point. There you go, that's that part, that branch of it. Remember, the axis of symmetry runs through the vertex. Because this parabola opens up, the vertex is the low point, the minimum. And to get a third point, and by the way, we need 3 points to plot any parabolas. One has to be the vertex, which is the turning point of the graph, right? And then we need 1 point on either branch of the parabola. This one I'm going to get by reflection. And there you have it. This would be the graph of this parabola. And just extend it above indefinitely. I'm okay with how it looks. So there you have it. That's going to be the graph of this parabola. Oops, sorry. That part of it. There you go. And we have the graph of it. So we have 2 points for reference. Remember, you need 3 points total. One must be the vertex. The other 2 points are optional. I use the y-intercept, which in this case was 0, 2. Now the x-intercepts, again, the points where the function crosses the x-axis. Okay, let's take a look at the x-intercept now. Okay, so how are we going to find the x-intercepts? Now, to find the x-intercepts in general, for any function, not linear, not quadratic necessarily, for any functions, we need to set the function equal to 0 and solve for x. So in this case, I'm going to set 3x squared plus 6x plus 2 equals 0. And I have a feeling that x-intercepts of this one are not going to be integers. Now, there's one way to check whether this function, by the way, the quadratic function, is factorable using integers or rational numbers. And we simply do b squared minus 4ac. And let me actually show the solution. This is how we're going to find them. Negative b plus minus b squared minus 4ac, which all of you remember this as the quadratic formula, correct? So that's what that is. So in order to use the quadratic formula, we need to identify the ABCs. Now, I usually, for a given quadratic function, I do b squared minus 4ac because it's not a waste of time anyhow. Notice the radicand is that. So if we have to use quadratic formula, we have to do the square root anyhow. So let's find out b squared minus 4ac. And remember, for this one, a is 3, b is 6, and c is 2. We identified those earlier for the other exercise as well. Remember this one? Sorry, there you go. We identified those earlier for the other problem. So let's do them for this one. Now, b squared, that's going to be 36 minus 4 times 3 times 2. That's 36 minus 24, or 12. Now, 12 is not a perfect square number. Not perfect square. Remember, perfect square numbers are numbers like 1, 4, 9, 16, right? Those are the square of the whole numbers or natural numbers. Well, when we say it's not perfect square, that means the square root of 12 doesn't equal to a whole number. That's what that means. It's not a perfect square. So if the number is not perfect square, that means this is not factorable. So we have to use quadratic formula anyhow. Over 2a, so that's going to be 2 times 3b is 6, negative 6 plus or minus, and we just did b squared minus 4ac. See that? Now, let's tidy up this thing a little bit. Square root of 12, by the way, that's 4 times 3. I can take square root of 4 becomes 2. That's 2 rad 3. Therefore, the expression is negative 6 plus or minus 2 square root of 3 divided by 6. Now, the way you work this one, you got to be careful. Don't do this, because some students actually do that, and what they get is plus or minus 2 root 3, which is incorrect. Right? We could cancel, but we're not canceling them correctly. So the way to do this correctly is the following. You need to divide negative 6 by 6 as well as plus or minus 2 root 3 divided by 6. See, both terms divide by 6, not just the first one. So this gives me negative 1 plus or minus 2 6. That's going to be 1/3. That's plus minus 3 over root 3. Or square root of 3 over 3. Now, square root of 3 over 3, this one, we got to work it on the calculator. But there were two solutions out of this one. The exact numbers are negative 1 plus root 3 over 3 and negative 1 minus root 3 over 3. Those are the exact values. Okay. Now, the approximation to these, the top one is about negative 0.42-ish. The bottom is about negative 1.6-ish. All right, and that's going to help me for my graphs. And there you go. The negative 0.42, that's the lower number. That's this one. So I'm just going to, on my graph, though, I'm going to put the exact coordinates, right? It's going to be negative 1 plus root 3 over 3. Those are the exact coordinates. And the lower number is negative 1 minus root 3 over 3. That's negative 1 minus root 3 over 3. You see that? So those become the x-intercepts. All right. And what else do we need? Let's do concave up and down. This one is going to be concave up. because it opens upward, concave up. And then we did the x-intercepts. How about the y-intercept? We did graph it. Let's do domain and range. Again, domain of quadratic function is always all real numbers regardless of the form. And you can see x can be anything. There's going to be an output for it. The range, however, for this one, if you look at the range now, the lowest number it can be is -1, the function. And it just goes up forever, right? For range, we look at the y-axis. Therefore, there is no point lower than -1 on the y-axis. So that's going to make up our range. The range is from -1 to infinity. All right. Let's do increasing, decreasing. Again, as you go from left to right, see how you slide. So from -infinity up to, x -1, it's decreasing, and then from -1 and beyond, it's going to rise, going to be increasing. And those become the interval for increasing, decreasing. So decreases up to -1. I'm going to write that. It's going to be decreasing on the x-axis from -infinity to -1. And then it's going to be increasing, moving upwards from -1 to infinity. Okay, and where is the function positive and negative? Well, anywhere the function is above the x-axis, so that would be right in here. It's positive here and positive there, right? Both of those sits above the x-axis. And then where is it negative? Where it falls below the x-axis, right? Right in here, the red, negative. Now, my red, I said red, but I did green, sorry. And there you go. Now it's red. Okay. Therefore, between the x-intercepts, it's negative, correct? Between the x-intercepts is negative. Outside of those is positive. And we're going to write that. So the function f of x is a positive from -infinity up to -1 minus √3/3. Don't put brackets here as parentheses because at that point it is 0. We want it to be above 0. Union to the right of the other intercept, correct? Which is -1 plus √3/3. So that's going to go from -1 plus √3/3 to infinity. And the function is going to be negative, again, between the intercepts. That's between -1 minus √3/3 and -1 plus √3/3. All right. And there we have it. Ladies and gentlemen, everything is good. The complete analysis of the quadratic function. All right, I think you're going to be okay now to do your exercises. But we are done with this lecture, and thank you for watching.